Alright, so today what we want to talk about is a dampening periodic curve. So if you think about a spring, obviously if you take a spring and you were to release it, it's not going to keep going up and down forever. I mean, just gravity alone, it's going to slowly dampen. And so we're going to look at what happens when it dampens, okay? We get an E in there with a negative CT. And C deals with the springiness of the spring. The larger the spring is, the stiffer the spring. The smaller the C, then the looser the spring, all right? So let's take a look at our notes. So first of all, example 1, two springs are experiencing dampening harmonic motion, both at 0.5 cycles per second and both with an initial displacement of 10. The first spring has a dampening constant of 0.5 and the second has a dampening constant of 0.1, okay? So dampening constant, that's our C, all right? That's our C, and that's our C, all right? So find a function model of both springs. Well, let's go back to our equations. I'm either going to have the sine or the cosine, but I think we're going to start with cosine because we're going to pull the spring up. In fact, if we do a real quick kind of like little graph, we'll have an idea. So we're going to start up at 10. So I'm going to go by 2, 4, 6, 8, 10, right? I'll do the same thing on the other one. 2, 4, 6, 8, 10. We're going to start up at 10 and release it. So for both of them, I'm going to go with a cosine, and I'm going to go with both of them to have the amplitude of 10. All right, so let's go y equals a 10. And we're going to have to put in our e to the negative, and the c for the first spring is going to be 0.5 t. And I want to use a cosine because we're going to start up here, okay? 0.5 cycles per second, right? So that means it's going to go and do its full revolution in half a second. So let's make a little sketch. That always helps me. So if I go 0.1, 2, if I go 0.1, 2, 3, 4, 5, there's 0.5, 0.6, 7, 8, 9, 10, which is 1 second, right? 1, 2, 3, 4, 5, there's 0.5, 1, 2, 3, and it's going to off the page, but that's okay. At least I've got 1, okay? So within half a second, it's going to make a full revolution, right? So it's going to look something like this. And I'm going to just make a little sketch here because I want to find out what the height of this is. But I'll use my calculator to get the height. So I do know it's going to have this shape, and this one over here is going to do the same kind of thing. I'm going to start up at 10. This one's going to be a little looser, so it won't. Actually, I kind of drew it wrong. Let me draw them both a little bit better. It's worth redrawing it. Okay. This one's going to be tighter, so it's going to actually dampen more quickly. So this one's going to be more like that, and this one's going to be looser, so it's really going to be more like that. You see the difference? This one's going to be a stiffer curve because it's going to bounce and come back to equilibrium more quickly than this one. But I don't know these exact values, but I can find out. So let me get my equations. So first of all, I'm going to go cosine. Well, my period is going to be my frequency is 0.5. So to find b for both of them, we're going to take our 2 pi, we're going to divide it by 0.5, right? We take our always 2 pi divided by the length of the curve. Well, it says the first spring, it says they both are at 0.5 cycles per second. 0.5 means it's going to go through its full revolution in half a second. Nika's going to be wide awake. Yeah. You're still on European time, aren't you? There you go. So we end up with getting b to be 4 pi. Okay, and if you don't believe me, you can do the math. 2 divided by 0.5 is 4, right? So we get a 4 pi t. Okay, there's the equation for the first one. And the second one is going to have the exact same equation, except we're going to use a 0.1 here. So we'll go y equals a 10 e negative 0.1 t to the cosine of 4 pi t. There's my second equation, all right? Now, what I'd like to know is what is the value for its second height. And we'll find, if we can find out the value at its lowest spot and its highest spot, then we can graph this pretty easily. One of the ways we can do that is just using a calculator, right? And get the values. Now, if I'm going to use my calculator, because I really want, if I'm going to graph it, I know this value. I don't really know the height. I don't really know the height when it's at its lowest, right? And I don't really know the height at its highest up here because it's dampening, right? Yeah, Ryan?
What does going negative represent for the spring?
This negative here,
No, like on the graph, how does the spring go negative?
back your negative time. Is that what you mean, negative?
Go down below the x-axis.
Oh, right. So, sure, if it's a spring, so let's say you take the spring as right here and you pull it up. Does that make sense? You pull it up, and then when it goes down, it's going to oscillate up and down, but it's going to oscillate below and up from its equilibrium.
Oh, I see.
Does that make sense? I understand what you mean now, okay? Anyway, let's go ahead and do this. Okay, so first of all, mode, it's got to be radians. You guys agree? So let me first of all put in, so if one full cycle is at 0.5, let me do that one, and then I'll have to put in its 0.25 to find its lowest. So let's let t, first of all, let's let t equal 0.25, because 0.25 will get me its lowest. You guys agree with that?
Wait, so do you pick T or select?
Yeah, why did I pick 0.25? It's half, isn't it? It's half, and that would tell me when it's at its lowest, right? So let's go, okay, mode, quit, let's go 10. We're going to go e to the negative 0.5 times 0.25, right? Cosine of 4 pi times 0.25. So I've got 0.25 in for my time up here with e and also with the cosine. It's hit enter, okay? So it's about a negative 8.8, okay? That makes sense to me, right? 2, 4, 6, 8, 8.8. So it's going to be down about there, okay? All right, and put it up there. So it is going to dampen. It's not going to go all the way down to negative 10. It's going to go to a negative 8.8, okay? Now let's put in the 0.5. So I go 10, and I go e to the, I'm going to go negative 0.5 times 0.5, right? Cosine 4 pi times my 0.5, and I get an answer of about 7.78, okay? So 2, 4, 6, 8, 7.78 is here. So you can see it's going to start dampening. It's going to come down like this. It's going to go back up. Ooh, that's a bad looking graph. It's Monday. That's a really bad looking graph. Let's get this look a little bit better. There you go. The other curve is going to have the same behavior, but we'll find out what happens with it with the negative 0.1. So clear. We're going to go 10 e to the negative 0.1 times, let's do the 0.25 first, 0.25 times 0.25 cosine 4 pi times 0.25. Got an answer of a negative 9.7. So this one's looser, right? Here's negative 10. So at 0.25, it's almost 10, but a little bit looser. And let's let t equal 0.5. And I can then go to my 10, hit my e to the negative 0.1 times 0.25, oops, 0.5, my bad, cosine 4 pi times 0.5, and I get an answer about 9.5, okay? So 1, 2, 3, 4, 5. So it's a pretty loose spring. Hold on, get this back. There we go, and there we go. All right. Now, of course, if you're Ryan, and I would agree with Ryan in this case, why not just graph it and take a look at it, right? Which we can. So if we're going to graph this on the calculator, we've got to think about a couple of important things. One, the window. More importantly, let's think about the window, okay? Right now, on my calculator, I've got 0 to 2. That'll work. 2 seconds, right? I mean, after 1, it's here. 2 seconds is fine. -5, I'm going to have to go -10 for sure, but I might go -12 to 12. You guys okay with that? Right? Let's plug in my equation. So we got to go a 10 e to the -0.5x, which represents time, cosine 4 pi times x, right? Now let's see what it looks like. There it is. Look at that. And then by my trace button, I can get a lot of these values. There's 1, gives me a height at 1 second, right? So there it is at 1 second. There's my height. And it just continues. Let's go 2 seconds. 3. I mean, it does dampen. Let's take a look at the other one, okay? So if I do my 10 e to the -0.1 x cosine 4 pi x. Let's see what this one looks like, okay? Okay, it's a little bit more springy. You notice that? Okay, did you look at the two differences between the two? You can put them both on the same screen to see it, but this one's definitely more springy, huh? It tends to, keep its height a little bit longer, okay? All right, and then you can go to trace, 1 second, 9. I mean, it hasn't dissipated much, has it? You can go to 2, 8, okay? So this one's significantly different, right? And then we can just graph this in the rest of the way. We know it kind of looks a little less, and a little less, and a little less. I'm not being perfect on this, but the main thing I want to get is the idea that we could get it exact, but there you go. Okay? All right. Turn the page. All right. Okay, so Red, Diana, and Landon are all sitting on a Ferris wheel. Okay, there's Red, Diana, and Landon. Okay, and it's 3 feet up, right? Yeah. Are you ready for me? Yes.
Well, I did the warm-up. You might want to check my work.
I think the answer's on the back, though, aren't they?
Oh, I didn't even flip it over.
Yeah, flip it over, check. Yeah.
Let's see how we did.
Hopefully you guys did great. So, it's going to go 2 revolutions per minute. So what I want to do, before you do anything, I think having a graph of this really helps, okay? So, it's 5 meters from here, 3 here. So really, if you were to get on right here at the very bottom, because that's where you get on, right? You get on at 3, right? Get on at height of 3. And it's got a revolution every 2 minutes. So go 1 minute, 2 minutes, right? And so if I got on at 3, and then I'd go all the way around, and I'd get off after 2 minutes. Does that make sense? This is I'm going to say Bill's getting on here, and then my kids are going to get on after me. So we'll just start Bill here, okay? Yeah. So then halfway through, I'm going to be all the way at a height of 13. I see how why it's 13? 5 is 10, right? Plus is 3, so I'm all the way up at 13. So I'm all the way up here. So here's my ride. How's that? Now, for my equation, we'll just say Bill's equation. We're going to have y equals. I'm going to go with a negative cosine. You guys okay with that?
Yeah.
I'm going to go with a -5 cosine. Now, where did I get the 5 from?
Between 3 and 13.
I go up. I'm going to go 5s, or we can go max. If you want the amplitude, it's the max minus the min divided by 2, right? Which is 5, right? You guys agree with the amplitude?
Yeah.
Okay, now my B, or my frequency for Bill, is 2 pi divided by 2, right? Because it takes 2 minutes for one full cycle. So pi, right? For Bill, there is no horizontal shift. That's it. But let's take a look. This is pi fourths. This is pi halves. Red's all the way over here. Land is all the way over here. So let's do Diana first, because Diana's the next one to get on. So Diana is going to get on at pi halves later, right? So Diana's equation is just going to be a y equals a negative 5 cosine. We're going to go a pi, and we're going to go our t minus pi halves for Diana, because she just has a shift of pi halves. Pi force, pi halves. Can you see that shift? She's going to get on the roller coaster pi halves later. Okay. But as far as time, what's that time? It's going to take, so instead of pi halves, it's not really pi halves. It is, you ready? She gets on 1 minute later. How do I know that?
It's halfway.
It's halfway. So let's make it 1. Okay. Red then gets on the roller coaster. Let's see, there's 30 seconds. There's a minute, right? There's a minute 15. You guys read that? Minute 15. So red's is going to be a y equals a negative 5 cosine. And we're going to go our pi. And it's going to be 1.25. Oops, sorry, t. My bad. T minus 1.25. Okay, I'll do it again, okay? So if it's 2 minutes all the way around, right? 2 minutes all the way around, there is 15 seconds, 30, nope, I got that wrong. Half a minute, a minute. So it's a minute 15, which is 1.25, right, Nika? I know you're barely awake, aren't you? But sorry, we'll keep you going. How about Landon? Landon goes all the way around. You ready? He goes around. Yeah.
It says 2 revolutions per minute. Would that mean that each way around is only 30 seconds?
Oh my goodness, did I do that wrong?
I can't do it.
I'm going with the cosine because I'm starting down here. We could shift it. Yeah, that's just all horizontal shifts. Well, we got our vertical shift. Yeah, we got to have a vertical shift in there for sure. I haven't done that one yet. All right, should we start this one again? No big deal. We can start this one again.
The whole problem?
No,
With-
we only have to change the time.
We got to change a couple of things.
Isn't it just...
2 revolutions per minute means 1 revolution in 30 seconds, which is 0.5 minutes. Yes, I did make a mistake. I'm admitting it on film. My bad. It's okay. And there is a vertical shift of 8. All right. All right, I got some things to change. I did make a mistake. Doggone it. I know. Okay, so B. Let's go back to what B should be. B is really going to be 2 pi divided by 0.5, right? 2 pi divided by 0.5, which is 4 pi t. But then there is a vertical shift of 8. And how to get the 8? I know it's the minimum. So K is the minimum, which is 3, plus the amplitude, which is 5, which is 8. Okay, there's Bill. Sorry, guys. We'll get this fixed. No big deal. All right, so let's go back to... Let's fix Diana's first. Diana's going to have a 4 pi here. And then let's take and think about time. So if it's 30 seconds all the way around, right? So take my 30 seconds and divide it up into 1, 2, 3, 4, 5, 6, 7, 8 parts, right? What's 30 divided by 8? 30 divided by 8. Have I lost you? 3.75. 3.75 seconds, right? To here. 7.5 to here. And then 3 times my 3.5, 3 times my 3.75 is 11.25 to here. And 3.75 times 4. 15 seconds to here, which makes sense. So, and I add, that's an 18.75. Nope. Yeah. Okay. All right, now we can finish this up. Let's go back. Let's fix Diana's. -5 cosine 4 pi t, and Diana's was 15 seconds. We're going to go minus 15 plus 8. There we go. Got it. Alright, reds. Let's fix reds. Reds is going to be a -5 cosine 4 pi. And we're going to go t, and with red, it's 18.75 minus an 18.75 plus my 8. There's red. And Landon, let's do Landon. Y equals a -5 cosine 4 pi t minus, let's see, Landon, we could actually go backwards for his or all the way around. If I get on, he's actually the first one on, isn't he? Where's Landon? So he's a -3.75. So t minus 3.75 plus the 8. Okay. We're all three riders after 30 seconds right where they started, aren't they? Yeah. Where they started. Do you want me to go back through this again, you guys, slowly? Show you my mistake. Okay, I'll do it real quickly. Yeah, first mistake I made is I didn't read this right. It is 2 revolutions per minute, not 2 minutes per revolution. I read 2 minutes per revolution, so it really is 30 seconds. So half a minute, right? Which means if it takes half a minute to go all the way around, that means if that's 30 seconds, that would be 15 seconds, right? That'd be 7.5 seconds. And then that's how I got my phase shift. I also knew that it had a vertical shift because the middle of the curve is right here. And the way I get the K is always the minimum plus the amplitude, so I had to add that one in there, okay? So, anyway, I'm going to have you guys work on this. I'm going to run next door, see how those guys are doing.